Ever looked at your solar panels on like a really rainy day and thought, well, that's a missed opportunity? Or, why does a bit of dust cut the power so much? Today, we're diving into this really fascinating white paper. It's called Rain-Powered Solar Panels in Salt Lake City. Our mission is to pull out the key insights, maybe some surprising facts too. Okay, let's unpack this.
Yeah, it's genuinely captivating stuff. I mean, the whole idea of harvesting energy not just from the sun, but from rain too, that's a pretty big step towards, well, truly all-weather renewable systems, more resilient.
Right. So it could help overcome some of those classic solar limitations.
Exactly. This deep dive really shows us how.
So how does this actually work? What are the main mechanisms, the innovations that let you get power from raindrops?
Well, what's interesting is it's not just one thing. It's kind of a multi-pronged approach. First up, you have these things called triboelectric nanogenerators.
TINGs.
TENGs, okay. Yeah. Think of them as really tiny friction generators. So when a raindrop hits the panel.
Ah, friction, like static electricity. Sort of, yeah. The friction between the water and the ting surface, it generates a small electrical charge. Basically, it's converting the physical impact of the rain directly into usable energy.
Huh. So capturing the force of the rain, that's different.
It really is. And it means solar shifts from being just a fair weather friend to potentially an all-weather power source.
Yeah.
That really improves reliability, especially on days when traditional panels just, dip.
Okay, so that's the rain impact part. What else is involved?
Right, then there are these hybrid rainwater harvesting systems. They basically collect rainwater from under the panels, and that water can then be treated and used to cool the panels down.
Cooling them helps.
Oh, yeah. It can boost the energy output by maybe 2 to 5%, especially important in hot climates. And then there's the more experimental side, graphene enhancements.
Graphene. Heard a lot about that material.
Exactly. Panels with special graphene layers can also generate some electricity from raindrop interactions. But, currently the output's still really minimal. We're talking picowatt scales.
Picowatts. So tiny. A trillionth of a watt.
Yeah, definitely experimental for now, but it shows future potential. And all this stuff integrates with the standard solar PV arrays and, crucially, energy storage systems to keep things stable for the grid.
It's quite a mix of technologies working together. Okay, so how does this apply somewhere specific? Let's zoom in on Salt Lake City like the paper does. Why is SLC considered a good place for this? And I guess what are the unique climate challenges there?
Well, Salt Lake City's climate is pretty interesting for this. It gets, modest rainfall, about 15.5 inches a year. So there's some potential there for the rain harvesting part.
Okay, modest rain.
But it gets a lot of snow, almost 52 inches annually. So any system there needs to be tough, snow resistant, and probably need regular maintenance in winter.
Right, snow load is a big deal.
Definitely. And then summers, temperatures can get over 100 degrees Fahrenheit. That actually helps PV efficiency sometimes, but overheating is a risk. So those cooling systems we mentioned, they become really beneficial.
Makes sense. Any other SLC-specific challenges?
Yeah, two big ones. Dust accumulation is a major headache. It can cut PV efficiency by like 6 to 11%.
Wow, that much.
And Salt Lake City also gets those winter inversions, where warm air traps cold, polluted air near the ground.
Oh, right, the smog.
Exactly. That smog layer can significantly reduce the sunlight actually reaching the panels. So it's a complex environment.
Okay, so the tech is cool. SLC is a unique test case. But it always comes down to the economics, doesn't it? Here's where it gets really interesting. What are the costs? And crucially, what's the return on investment look like compared to just standard solar?
Right, this is key. So your typical residential solar PV system costs around $2.74 per watt to install right now, give or take. These rain-enhanced systems with the extra tens and maybe cooling, they're understandably pricier up front, estimated between, say, $3.15 and $5.19 per watt.
Okay, so a higher initial cost.
Yes. But, and this is the big but, the return on investment looks potentially much better. There's a hypothetical case study in the paper for a house in downtown SLC. It projects an ROI period of just 7 to 10 years for these hybrid systems.
7 to 10 years. Wow. Compared to what for traditional?
Compared to maybe 12 to 15 years for traditional systems in that same environment. So significantly faster payback.
That really changes the calculation.
It does. It makes solar potentially viable even with higher starting costs, especially in places that aren't perfectly sunny year-round. The study projects annual savings for the homeowner of $1,200 to $1,800. And get this, they even mentioned finding local Reddit users talking about their energy bills dropping to like $12, $15 a month after getting solar installed there. Real-world numbers backing it up.
$12 a month. Okay, that's compelling. But surely there are hurdles, right? What's stopping this from being everywhere already? What's the future hold?
Absolutely, there are barriers. The main one is still that higher upfront cost, especially for the tank components and the necessary energy storage. And in places like SLC, with only modest rain, you might even need supplemental water for those cooling systems if you scale them up big time.
Right, can't always rely on the rain.
And the dust issue needs managing. That means automated cleaning systems, which add maintenance costs around $22 per kilowatt per year. It adds up.
Okay, so costs, water, dust, how do we overcome those?
Well, the innovation pathways are pretty clear. State and federal tax credits are huge. They can cover 30, maybe even 45% of installation costs, which makes a massive difference. Plus, there's ongoing research into making things like graphene production much cheaper. If that happens, the rain harvesting part gets more scalable.
So what does this all mean? If we pull it all together, it sounds like these rain-enhanced systems are combining different techs, kinetic energy, smart water use, storage, all to create something more reliable, works in more weather conditions. You pay more initially, but the faster ROI and long-term savings, plus that resilience, that seems like the trade-off for you, the homeowner.
Exactly. It really balances those factors. And, it raises a bigger question, doesn't it? As we keep pushing the limits of renewables, what other, maybe unexpected combinations of technologies out there might hold the key to getting truly uninterrupted, truly resilient power for our future?